Welcome to our second lecture on the course Solar Electric Energy Systems. We talked about potential irradiance and shadowing and so on in the last lecture. Today we'll talk about solar concentration and solar thermal systems. So solar thermal systems are known for a quite long time. Here even quite advanced solar thermal systems at the World Exhibition in Paris in 1889 with a parabolic concentrator, steam generator, and on the left here you see a steam engine which is driving a printing press and got lots of success during that time. And also smaller systems. First flat plate collector was patented in 1910, so it's a quite established technology. But today we talk about concentration. So we have here as an example the parabolic concentrator. So you have the effective area from the sun coming in. In general, a parabolic concentrator can only concentrate direct solar irradiance. It cannot make use of diffuse irradiance. So we have the effective area. The irradiance is then reflected on the focus area here. Here the absorber area could be a point or could be an area, and according to that you see we have the concentration ratio, which is the absorber area divided by the aperture area. You don't have to make a single mirror like you see here on the bottom. Can also make a parabolic truck, so you don't have a focus point, you have a focus line here. Also you can split off the parabolic form in different reflectors, or make even several small reflectors. The only thing is that they have to be attached in a tangential form around the parabolic form. Then they must be positioned in that way that all incoming light is reflected towards the focus point or the absorber. Here you see the different concentration ratios, starting with 1, that means no concentration, that's a conventional flat plate absorber, and it is able to achieve a temperature in the vicinity of 160, 180 degrees. And sure, at this efficiency, if you have a collector and you want to achieve the maximum temperature, you shouldn't push any water through it, and therefore the collector efficiency is 0. If you let flow a lot of water through it, then efficiency goes up, but then the achievable temperature is much lower. So if you follow this line going up, then temperature is higher because you profit from all the thermal energy there, but achievable temperature is very low. If you go to higher concentration ratio, for example 10 here, temperature is much higher, so it can be above 500 degrees. If you have an acceptable efficiency, you should count on 300 degrees or so, and so on. So you concentrate more and more, and you can have really high temperatures. The theoretical maximum is the temperature of the surface of the sun. So it's not possible thermodynamically to achieve higher temperature than your source, which is the sun, and this is 5770 Kelvin. And there you have to have a concentration rate of about 30,000. Here you see an example, interestingly from the 50s and 60s in southern France. Before France started to invest a lot of nuclear energy, they were very well advanced in solar energy. And if you go, if the opportunity to go there, it's on the border to Spain and the Pyrenees. It's called Four Solaire in Odeo. And this is a quite high building here, about 40 meters. And in front of that building, there are 63 plane mirrors, which direct the changing sunlight They are always tracked to the sunlight, and they direct it in such a way that that the sun rays go in parallel to this big parabolic mirror. And then you have a concentration here, the end of a factor of 16,000 concentration ratio. That means you have a power density of 1.6 kilowatt per square centimeters, not per square meter, per square centimeters. That's really a lot. And the maximum achieved temperature there was 3000 degrees Celsius, and efficiency was about 60%. Um, it has been used in the beginning for producing steam and powering a steam generator. Nowadays, it's used for metallurgy because you can switch quickly off and on the power source, the mirrors, and then you can have different mixtures of metals and so on, treat them with different temperature, and therefore it's still under operation. It's a bit newer example from 1985 in the Mojave Desert in Arizona in the United States. It's been built during the government of Jimmy Carter there, and it was for a very long time the largest of solar energy plant in the world. In end stage, it had about 354 megawatts electric, with a mirror area of 2.6 square kilometers. Interestingly, the mirrors have not been made in the United States. They came from Germany, from the company Schott. They require a lot of cleaning because there's sand and so on, so the operations costs are relatively high. At the end, the total electricity costs have been around 10 cents per kilowatt hour. And in comparison to photovoltaics nowadays, that is quite a lot. So the last quotes for, I think it was a big Qatar power plant, the last offers there have been in the vicinity of 1.4 cent per kilowatt hour for photovoltaic power plants. So let's go into the power flow. So the first part you know very well, incoming irradiance. We have been discussing this a lot in the last lectures. Then you have the reflector. There's something lost because it's not perfect reflection here. This is the index rho. And then it hits the absorber. There's also some losses there. Usually the reflector is quite close to the absorber. But for example, if you have a tower power plant, then this could be in some distance here. So we saw here before. So this could be some 100 meters, and therefore could be even some losses here. And this is mentioned here. And then you have the absorber, which is protected via, for example, here um, a glass tube here. And when the absorption is not perfect, you try to make this alpha as high as possible to achieve the maximum absorption. And here it's converted the incoming irradiance into heat. You try to profit a lot from this generated heat, but you have some losses. For example, thermal radiation um, or convective heat transfer. Depends. Sometimes you have this glass tube evacuated, so you have a vacuum inside. So inside there is no convective heat transfer, but outside there's a convective heat transfer. So a cold air comes here, it gets heated up, density gets lighter, so it flows up. And therefore you have a quite a high share of convective heat transfer. You don't have to concentrate via parabolic mirrors. You can also use lenses, or kind of flat lenses called Fresnel lenses. In general, if you take a look at the scheme of energy flow, so we have here talked about a lot about the incoming irradiance and some part is reflected. So then we have the solar energy converter here, which also requires some energy to be produced, the so-called gray energy. And in photovoltaics, what we discussed next lecture, this is the green energy flow, this is the electric output. General, what we discussed today is the thermal flow, so small q we use for that. So we can either store that energy or we can take away. We have water flow, or in general the lower ones are losses. So conduction due to the imperfect damping. You have radiation, that is thermal radiation with the surface temperature of the collector, or convection, as I just mentioned. Here you see it as a typical loss mechanisms in a solar thermal a flat plate collector, so without concentration. So we see here we have a reflection, that's a cover. Usually we have, if you come from air to glass, you have a reflection here at the first interface about 4%. Depending on the thickness and the quality of the glass and the incidence angle, you have some absorption in the glass, typically 2%. And then at the next interface from glass back to air, you have typically another 4% of losses. So in totally, it's about 8% of losses at the first cover sheet. If you have two cover sheets, it's a double. Usually nowadays we have only one cover sheet, and then it hits the absorber. As I told, the absorption is not perfect, so we have some losses there. Here about 8%. And then also we have some, first then it gets transformed into thermal heat flow. So we profit 60% of that. So this is our efficiency here. But we have also losses, thermal losses here. This is thermal conduction, but also a thermal radiation from the absorber plate here. This can be reduced by the cover glass. So usually glass is transparent for the visible part or for sunlight, but not transparent for the infrared part being emitted from the absorber, the typical greenhouse effect what you see here. Plus we have the natural convection losses. As I mentioned, just cold air is heating up, it is lifted, the buoyancy occurs, and new cold air comes, and we have this natural convection flow here. You can eliminate that by taking away the air here. So if there's no air, there's no natural convection. This is called vacuum collector. But on the other hand, you need a much thicker glass, a cover glass, or even a tube in order to withstand the pressure. So this is the upper one. This is a reflection, and a reflection at the absorber and absorption in the cover glass we call optical losses. The lower ones here, the conduction and natural convection and the thermal radiation, these are called thermal losses at the collector. So you see here an overview here. So we have here on the x-axis the temperature difference between a collector and ambient. On the y-axis we have the relative conversion efficiency. The blue part here are the optical losses. They are independent from the temperature difference. So you see here it's in the vicinity of 84% or 83%. Is a remaining relative conversion efficiency, so we lose about 16% due to the optical losses. And then depending on the temperature, so sure, if you have no temperature difference here, there are no thermal losses, so you just have the optical losses. But as you increase the temperature, depending on the construction, we come to this later a bit on the of the collector, this increase. It's a bit non-linear because if you have high temperature difference, the thermal conduction is linear, but for the thermal radiation, it goes up with a power of 4. And so therefore this is a bit curved a bit and not straight here. Here you see for an irradiance value of 1000 watt per square meter, you see this curve, so you achieve temperatures well above 100 degree Kelvin, temperature difference about 100 degree Kelvin, and still have acceptable conversion efficiency. If the irradiance goes down, for example, winter, you hardly, even if with very low conversion efficiency, you hardly arrive at 40 degrees of temperature differences. Here we see the different types of solar thermal collectors. The red line, as I mentioned already, this is a vacuum tube collector. So we have very limited, or we have no um, convection here, and therefore the thermal losses are pretty much reduced. We principally have only conduction losses and thermal radiation losses, so you can achieve very high temperatures, well above 200 degrees. And the opposite, we have an uncovered absorber, so it's just a black tube here without any glass, and so this has this curve. Interestingly, you see here the optical losses are quite low. That's because you don't have any glass sheet, so there's no losses, no optical losses at the glass sheet. You just have the 9% absorption losses here at the surface of your absorber. Um, but then the thermal losses are really, really high, and then temperature is sinking pretty quickly. And yes, you still can make use of this collector. For example, it's very often used at public swimming pools where you just have to increase temperature maybe by 5 degrees, and it's cheap. And in this operation range, it's even better than the more efficient flat plate collectors. And the, so it has its existence here, this uncovered absorber. But let's take a look at the flat plate collectors. So if you want to have a good efficiency, you take a two glass collector, so you limit the thermal losses there. But on the other hand, as you see here, you have a very high quantity of optical losses here because due to the reflection on the interfaces between the different glass sheets and air. And so it just makes sense if you have quite high temperature differences. Then we have two kinds of flat plate collectors, both with one glass, but one is called selective and the other called non-selective. Here the dark blue here, that is that one, and the selective apparently is much better, and I'll explain you now how this works. So here we have an logarithmic representation of the wavelength here. Here the maximum of this is the solar radiation here. This is the sun considered as a black body, and the maximum of emission is in the vicinity of 500 nanometers or 0.5 micrometers here. It seems to be symmetrical. As you saw with a linear scale, it looks much different. And then you have this black line is a non-selective absorber, so it absorbs all at the pretty much close to 1. So it absorbs in the visible range, but also here, as you see here, 10 micrometers, that's the infrared range. So it absorbs all the same. And there is a law that says that the absorption is equal to the emission index. So this alpha is equal to epsilon. And so that means he has a good absorption, but in the infrared range, it has good absorption. That means, but also has a high emission. So that means the infrared radiation is emitted very well. So we have a very high quantity of losses here in the 10 micrometer range. This is a black body radiation at 350 Kelvin, which is a typical surface temperature of an absorber, of a non-concentrating flat plate collector absorber. So what can we do? We make a so-called selective absorber. That means it's pretty much the same properties in the visible range, where we have all we can absorb all the sun radiance, which goes up to 2 micrometers maybe. And then this changes its properties. Then the absorption goes down. That means also that the emission is going down also. So we have here quite a low emission and low absorption. And that means we avoid thermal losses. Sure, we cannot absorb anymore, but there's no solar irradiance anyway there. So in general, we have a big increase in efficiency here. As you see here, this middle blue line is well above the dark blue line here. So we can achieve much higher temperatures. It's mentioned the conversion efficiency. It's a bit astonishing because at the highest temperature you have the lowest efficiency. This is controlled by the flux of water. So if you have the so-called still stamped temperature, so you block the flux of water, then you achieve the highest temperature. But if you don't take away some of the hot water, then efficiency is sure it's close to zero. While you have the highest efficiency here at the lowest temperature, you push a lot of water through the pipes, and there's not really a lot of time to heat up. But in general, the thermal losses are low, and therefore you have a high conversion efficiency. That explains this bit first, at the first sight, a bit strange behavior at the relative conversion efficiencies. So this is a very typical thermosiphon system. So you have the collector, and then you don't have a pump or something like this, just due to the fact that the heated water is lighter than the cold water. It automatically flows up the water. It's called buoyancy, and then we have here the hot water, which flows inside the storage tank here. Um, the power of this flow is very low, so the height is very limited, so about 50 centimeters, and also you cannot make a lot of curve with this pipe, so the pipe has to be pretty straight. Otherwise it won't work. So the auto circulation won't work. You see a lot of projects like this because people don't care about this, and they installed a thermal collector, but they didn't consider the limited height and the necessity to install a straight pipe here. Um, and then it won't work. And the end you have a hot water tank. Not a, yes, it's both hot and cold water tank actually. So, but while the flow is very slow, you can have a very good stratification here. So the upper part is filled up with hot water, and the lower part is filled up with cold water. Um, and astonishingly, the water doesn't mix a lot. If you don't have quick movements with the water, it stays like this, and you can take away the heated water and fill up the cold water on the lower part. Some examples here. Here you see the attached storage here. Typical collector size for families between 2 and 2.5 square meters. I think this is a Turkish brand. It's also exported to Brazil. It's about 800 euros. Complete system. Weighs 42 kilograms, and you have the still temperature of 200 degrees Celsius. So another example seen in Portugal. On the right side is a local produced system. On the left side is astonishingly imported from Australia, solar hard system. This is seen in Brazil. Also, this is integrated, so the storage system is directly attached to the collector. In Germany, the thermosiphons principles are not possible because in winter we have very cold outdoor temperatures, and the water inside the collector would freeze and would destroy the collector. So equivalent to a car cooling system, we have to have a medium with a mixture of glycol to withstand the cold temperature. Usually it's designed to go down to minus 25 degrees and so on. It works, but you cannot use glycol for taking a shower. So you have to do a heat exchange of the heated glycol with the conventional water here. And while the heat exchanger requires some pressure, it's not possible anymore with the thermosiphon principle. So you have to have an extra pump there and an extra control because you cannot let run the pump for 24 hours, because in nighttime you would have the opposite effect. Outdoor could be very cold and you would cool down your storage tank. So you should switch off your collector, and what you do, you take the temperature difference between the hot part of the collector and see whether it's still higher than the water in the water tank. If it's higher, you switch on the pump. If it's colder, you keep it shut, the switch here, and then there's no pumping. You wait until the temperature is increasing. So you have also the hot water storage as a stratification tank. You take off the hot water. Plus, if you have really cold days and a lot of little irradiance, you have an additional heater there. There's some simulation software, for example, here this T-Sol software package where you can really calculate uh, your um, your system with that. Was a PhD thesis at the Technical University in Berlin, and later became a quite big company there. For some time, it was even the most famous thermal simulation programs for solar thermal systems. Here's some description. So it's just described how this works. There's a front end where you can enter your components here, the collector and the storage system and so on, and then the different pipes and so on, additional components, additional heating. And then you have a description of the array. For example, here 6 collectors with 1 square meters each. Then you have a tank here with 300 liters, for example, here, and the height and so on. So it also calculates the stratification inside the tank and the losses if its stratification not perfect. And it carries out a simulation between 1 and 6 minutes. So it's just based on hourly climate data. Better if you have half an hour, minute data, and then it calculates the mass flows within every component and perform a step within 1 to 6 minutes. Yes, we have the tank layers, so the stratification inside the tank is also calculated. So you can start a simulation now. And so you see here represented by the different colors, and you see here on the lower left part, you see the time. So it's 5 o'clock in the morning. Now sun goes up at 7, 8 o'clock. It's heating up. It's getting orange. So you have about 40, 50 degrees. 10 o'clock now, you have already 60 degrees. Also, the tank is getting heated up. So the tank is not stratified anymore. It's as if almost equal temperature. And now we have in the afternoon, it's now 16 o'clock, 4 p.m. And then sun is setting, and then you take out water here, and from the lower part, cold water is entering, and you take up of the hot water, and then hopefully it's night. In the morning, then the hot water has been enough to supply hot water for the whole day. And so on. Now it's simulated a cold day without a lot of irradiance, and you see that the hot water reservoir is drastically decreasing. Then you have a nice presentation sheet for the results for the investor to see what components are you using and how much it costs, and how much is the return, what part of the energy you can get, and how much carbon dioxide emissions are saved. Here you see the solar contribution during the year. So the yellow part is a solar contribution. So you see here in the summer months, it's almost 100% contribution by solar. In winter, it's less. Then you can do also energy balance schematic. So you can take a look at the input and output of the different components. First starting with irradiance, how much irradiance is there. So that's 6.9 megawatt hours is coming in. And so you see all the different losses and the internal piping losses and the tank losses, the final energy and so on. Then there's some propaganda that it is now a nice user interface and so on. You can compare different principles and different components to each other. So here you can have a 1 tank compared to a 2 tank solution. You have a database which is updated with all the data from perhaps new types of inverters, new companies which develop new kinds of collectors, not inverters. Sorry. Here you see, for example, a base with Wagner collectors and the different sizes they have and so on, and the different properties. You can also use air collector systems. It's also possible, but the thermal capacity of air is very low, so you have to have a high throughput of the media, means air, so it's not as efficient as the as, it, liquid collectors. But it's possible if you have the opportunity. It calculates the profitability of such a system. Also, there's now news for the North American market, so they use all the Fahrenheit and gallons and so on. So it changes the unit and so on. And you have also from the North American market, there was some, but it's all the things that they have collected all data from all over the world, starting with irradiance, but also from the different components available in different countries. Here you have just additional heating. Sure, in Germany, for example, you need some additional heating because often the irradiance is not sufficient to run entirely on solar. Different languages are available: English, French, German, Italian. Then you have the integration of different sources for irradiance here. So you can select on a world map the location here and have a daily and yearly or seasonal change of irradiance and so on. Okay, that's not actually my XP, so it surely runs on Windows 10. We can skip that. So there is some calculation on it. Some music here also, whatever. So it shows again just this comprehensive profitability calculation, separate output of solar fraction. So you can compare different kinds of systems here as an example here. You see different locations and the global irradiance at each day, for example, here. Here, this is the final result. So you see the hot water contribution was 62%. I think the new version also has a nice photographic layout, so you can show to the housewives and so on, which usually don't like the collectors because it looks ugly, but you can discuss whether it's nice looking or not. So here you have another solution, so it's 50% only. And so you can here calculate the investment and the return of investment. And after here, for example, this example, it makes only profit after 16 years. It is a bit poor, but usually should get a quicker return of investment. So enough propaganda. You can also put it large scale. So here's an example from a solar energy generating system in the desert of Arizona. So you have a solar truck system with a focus line, and it's attached to storage there, so it can also run during nighttime. Usually don't use water there, not because of it's freezing. You use oil because you can heat up temperature up to 300 degrees Celsius without producing steam. You produce the steam then with a heat exchanger, and the high pressure steam goes here inside the turbine, powers a generator, and you power some houses. Then you go then you liquefy by condensing the steam here, and should be the pipe is going through here through the pulp, so it's not just because it was originally German and I put the English expression over it. And then you go via pump, and this increases the pressure. It consumes quite a lot of energy because you have to have create a high pressure here, and then additionally pressure is created by the steam generator here. You can also put an additional heater there, even in the desert. Sometimes there are clouds and so on, and then when the storage is empty, you can have additional gas powering, natural gas power heating then. In this case, at the ZEC systems, they even have a two-stage turbine, so they are not used going directly to the cooling tower. They use a second stage of the turbine in order to increase the turbine efficiency. Main thing is you have two cycles, so the solar cycles with a oil here, and the water steam cycles here. An additional thing to mention here is a convective air steam power plant. So you have here quite large area covered with glass or transparent plastics, and then the ground heats up, and the air is getting lighter, and it flows through a chimney, which can be quite large, could be some 100 meters high, and then it's powering turbine. This flow. There's been some experimental setups in southern Spain with 100 kilowatt, but there was original planning of I think almost 1 gigawatt power plant in the Australian desert with 1 kilometer of chimney, but it never been realized because meanwhile photovoltaic got so cheap and the constructive cost is quite high, so it's a bit stalled here. This is actually quite good idea, but due to the high constructive necessities, it's not developed further anymore. So we have here the idea with the so-called Desert Tech project in 2009. The basic idea was to generate electricity in North Africa by wind and solar, both with solar thermal systems, which cost 4 to 5 cents a kilowatt hours now. And due to the attached storage, you can have 8,000 full load hours per year. That means it's running through all the year. Or photovoltaics, which battery storage quite expensive, so it was just considered it works during daytime, and there you can achieve 2,000 to 2,500 full load hours. At this time, cost was estimated to 4 to 5 cents per kilowatt hour, but this is a cost you can achieve with photovoltaics now even in Germany with low irradiance levels. And for a high irradiance desert, you are in the vicinity 1 to 2 cents per kilowatt hour. So it got a bit stuck, the project. Anyway, it's quite good idea, but at the moment Morocco is built such a big system with 500 megawatt, but it uses basically the energy of its own on its own. So we didn't hear anything further on it. You have to consider also the transmission costs, which is quite optimistic here for 1 cent per kilowatt hour. Also goes here through Libya and Algeria, and so people, the investors, be afraid of investing there because they don't know whether investment is safe and so on, and therefore this got a bit stuck, this project. We have an exercise for that lecture. So first question is, which are the loss mechanisms at solar thermal energy systems? What is the advantage of solar thermal electric power systems in terms of possible storage compared to direct solar managed electricity conversion via photovoltaics? What are the two main technical disadvantages of concentrating power systems? What could be an advantage? If you take a look at the collectors from the page 70 to 73, a buyer has the option for two collectors. One with a selective coating, it's a bit more expensive. It costs 120 euros per square meter. Another with a non-selective absorber costs only 100 euro per square meter. And the idea is just he wants to know whether it makes sense to spend more money on the selective absorber when the required temperature difference is 50 Kelvin. Or the second part of the question is if it would be 75 Kelvin. Then another part of the exercise is what would be the generation cost in cents per kilowatt hour for solar thermal energy over lifetime, let's say 20 years. In Portugal, south of Portugal is Faro. There we have a global annual irradiance of 2000 kilowatt hours per square meter per year. Then we would consider a thermosiphon system, which consists of a flat plate collector with single glass cover and an effective area of 2 square meters. And this would cost there around 1,000 euros, including mounting. In Paderborn, we cannot apply a thermosiphon system, so we have to use a pumped system. And also the area has to be bigger, so we have considered a 4 square meter collector, and this is considered really more expensive. It costs about 5,000 euros. To compare both cases, and in both cases, the storage tank of the system is considered to be sufficient to accumulate and distribute all collected irradiance. So I made it a bit easier for you. Don't have to consider the storage size. So the question is, what has to be considered first besides the accumulated irradiance for an operation Paderborn when we calculate, we can consider a global irradiance during the year of 950 kilowatt hours on a square meter during a whole year. To select the adequate characteristics, so you choose the graph on page 73 that is closest to the average irradiance value for the whole year during daytime. This we discuss in the lecture in the exercise lecture. Then we have to consider also that the temperature, the time it needs to heat up such a thermal collector. Here we consider a size of 2.3 square meters. For example, the system we saw on page 74, the Turkish system, and to heat up the water inside the attached storage tank, which is also described there with a volume of 160 liters and a temperature, incoming temperature of 20 degrees, which is typical for tap water in the tropics, and you want to heat it up to 60 degrees Celsius. The temperature of the tap water should be considered to be equal to ambient temperature, and the temperature inside the collector is equal to the temperature inside the storage tank. So first we consider a constant irradiance value of 800 watt per square meter. Then we consider 400 watt per square meter, and last but not least we consider 200 watt per square meter only. Then we consider the irradiance efficiency graphs at page 73. The specific heat capacity of the water, you need that for the calculation, is 4.818 joule per gram Kelvin, and the water density is 1 million grams per cubic meter or 1,000 kilograms per cubic meter. And next question is how you can eventually get a different water temperature from a single storage tank. I explained it already several times. And what prerequisites are necessary. What else can you do if you need a lower water temperature than the water temperature inside the storage tank? For example, 30 inside instead of 60 degrees. That's the solution already. So we come to this a bit later. Or we can already start. The solutions are here, which are the loss mechanisms at solar thermal energy systems. So the optical losses at a typical flat plate collectors are, so we had reflection on the glass surface. We have absorption in the covering glass. Remember the graph here we saw that was about 2%. The reflection on both interfaces together are 8%. And we have reflection of irradiance leaving the cover glass. Also, this is here also, this is both 4%. So we have reflection on the glass surface 4%, absorption 2%, and the reflection of irradiance on the interface from the glass to the air again, 4%. Reflections at the absorber, I think it was 6% or so. Then we have the thermal losses. This is the heat conduction from absorber to the frame or the ground or the roof. Then we have convection, the natural convection. The warm air is lighter than the cold air, and it's lifted off from warm surfaces and is substituted then by flowing cold air. And the thermal radiation, so there is a radiation exchange between the warm surfaces and between the ground, especially between the sky. Here you see it again. So just as I mentioned here, here 8% means that both losses is 4% here and 4% here, absorption 2%, reflection at the absorber it's not 6%, 8%. It depends on the quality of the manufacturer and so on. And here the thermal radiation and the thermal conduction, and here 13% for the natural convection. The question was, what is the advantage of a solar thermal electrical power system in terms of possible storage compared to direct solar electricity conversions via photovoltaics? So we have here a solar thermal energy can be easily stored in a thermal storage, for example in a water tank or phase change material. Costs are about 5 cents per kilowatt hour of storage. So sometimes they are more expensive, or often they are more expensive than the actual generation of solar thermal energy. Electrical storage is much more difficult and more expensive. For small scale storage is in the vicinity of 15 cents per kilowatt hour for small scale storage. If you go to large scale storage, for example, pump hydropower plants, prices may go down to 5 cents per kilowatt hour. Next question was, what are the two main technical disadvantages of concentrating power system? What could be an advantage? This was that you can only use the direct part of solar irradiance. That is weather and site dependent, sure, and the reflectors or the lenses have to be tracked according to the position of the sun. Plus, you have to also keep the mirrors and the lenses clean because they are very sensible to that. Advantages is that the higher temperatures can be achieved that allow some applications and the so-called Carnot efficiency, which is highly dependent on the temperature difference. And if you have a high temperature difference, then you have a high conversion efficiency. So this is a Carnot efficiency, if you know from thermodynamics, or if you listen to my lecture on Energietechnik, we discussed also a lot about it. So it's 1 minus the T ambient divided by T collector, or not T ambient, or the T output of the system. So now we do some calculations about investment. So we have the selective collector with 120 euros per square meter, and a non-selective absorber at 100 euros per square meter, and the two temperatures, 50 Kelvin and 75 Kelvin of not temperature but temperature difference. And we take a look at the curves again. So we have here the different types of solar collectors, and here you see the vacuum collector. Sure, it stays at high temperature for a long time, it had optical losses, and also the constructive means are more excessive. And what we compare here is the middle blue and the middle blue and the dark blue line here. And so we take a look here. So we have here temperature difference of 50 Kelvin for the dark blue, so non-selective absorber. We have a conversion efficiency of 40%. And if we go up here, for the same temperature difference, but to the collector with a selective absorber, we have a conversion efficiency of 54%. So advantage. And for the 75 degrees of temperature difference, we have about 11% of conversion efficiency for the non-selective absorber, and for the selective absorber we have here 39% of conversion efficiency. So let us see whether it pays off. So we took from the graph here the conversion efficiency at 50 degrees. We saw a 40% of conversion efficiency for the non-selective absorber and 54% at the selective absorber. At 75 Kelvin temperature difference, we see exactly the number is 11.5% of conversion efficiency, while the conversion efficiency with the selective absorber is significantly higher, speaking 39%. So we take a look. So from the graph we can read that the relative cost is the cost per square meter, and the conversion efficiency. So we have here about 250 euro for an ideal collector that would convert everything into thermal energy, while it's for the selective absorber, the area required, it's less, and also the costs are less, 222 euro per square meter. At 75 Kelvin temperature difference, we have then 870 euro per square meter, and while we have at the selective absorber, we have 307 euro per square meter only. So I just have took for granted the cost of generated energy is proportional to the purchase price of the collector, reversibly proportional to the conversion efficiency. So we come to the next part of the exercise. So we have here, the question was about the generation costs in Seville, Spain. It's now Seville, we didn't take Faro, but it's about the same irradiance value. So we have here the yearly irradiance is in Seville 1944 kilowatt hours per square meter per year. If we take it for 365 days and 12 hours, so we have an average, so we take only from the morning to the evening, we not take 24 hours, we take just the daylight hours, and it's about 400 watt per square meter, and then we choose a graph with the 400 watt per square meter. That means we would have an efficiency of 37%, and then Paderborn irradiance is only half of that, speaking 950 kilowatt hours per square meter per year. And for the days and for the 365 days during daytime, this is equivalent to 216.9 watt per square meter. So therefore we choose the 200 watt per square meter graph, and for the required 400 Kelvin of conversion efficiency, it's interestingly doesn't reach that value. So we can not use that on average. So we have to use a different technical solutions, for example, a vacuum collector. So here we can read here the temperature difference here at 200 watt per square meter. And then we have the conversion efficiency here, and 37%. And we have the generation over 20 years. That means we have this irradiance value for the whole year times 2 square meter times the average conversion efficiency multiplied by 20 years. So we have about generation of 28.77 megawatt hours. In general, the calculation is very rough. If you want to do really very precise calculation, you should use a simulation programs just as TSOL. Um, Then the specific costs are, so we have the investment costs, which is about €1,000, and the generated heat during those 20 years. So we have a generation cost of about 3.848 cent per kilowatt hour of thermal energy. So the specific costs are already higher than PV electricity. If you consider the last tenders of the electricity companies in Portugal, there have been offers about 1.5 cent per kilowatt hour of electrical power. You have also the costly installation, the hot heat pipes. So this is therefore I'm very brief now with the solar thermal systems. I would spend more time on PV electricity. So we take a look at the warming up, so more in the dynamic part. We take a look at the area of 2.3 square meters and a volume of 160 liters. And we heat it up from tap water from 20 degrees to 60 degrees here. And yes, we take into consideration a constant irradiance of 800 watt per square meter, which is quite idealistic. They never have a constant irradiance, but we saw if we come very close to the Seville location of 400 watt per square meter. And 200 watt is just like Paderborn's average irradiance. We see here the heat required and the heat provided by solar, and you have to just match this. So the required heat has to be covered by solar. We calculate it now. This time required to achieve that is here the temperature difference multiplied by the heat capacity of the water times the volume times the density of the water rho, and the irradiance value E, and the area and the conversion efficiency at a certain irradiance value. And if you put in the numbers, so we have here from the, chapter 261, we have a temperature difference of 40 Kelvin, and the thermal capacity of 4.18 joule, can also translate in watt seconds per gram Kelvin. And we have the water density and the tank size. Yes, it's 160 liters. That is equal to 0.16 cubic meter. And the first part, we have the irradiance value of 800 watt per square meter, and the conversion efficiency is quite high, as 63%. If you take it out from the graph, so it would to complete the complete tank, it would require about 6.41 hour. So this efficiency was taken from page 70. For the next stage, if you only would have an irradiance of 400 watt per square meter, it's basically the same calculation. We just have the lower irradiance plus lower efficiency. We have to consider the lower efficiency also. So it's not only double the time, it's almost 3 times the time we need to heat it up, 18.78 hours. And if we go to the very low irradiance, just like the average irradiance in Paderborn, it would even require more than 400 hours to heat it up. So how you can get eventually different water temperatures. So I was talking about a lot of time, so you can do it by stratification inside the tank. So if there's a little water movement only in the tank, the hot water stays on the top and it can be extracted from the top, while you can fill up cold water on the lower tank part of the tank. Um, Usually, as a prerequisite, you have to have a tank with preferably a large vertical extension and a little water movement. Usually, they are mounted horizontally, which is not the best thermodynamically, but due to space limitations. The cooling can be achieved by operating the solar system as nighttime. So we can provide cooling by thermal radiation exchange with the sky or by water evaporation. Is this mentioned cooling? No, it's not mentioned cooling. Ah, yes, you need no temperature. Yes, cooling. Yes, we can do it or to can mixture. Ah, yes. Okay, that's it. Thanks a lot, and we see us next week.